Welcome to question 5 of the 2016 Mathematical Methods Exam 1 for the Southern Hemisphere. In this video we will be looking at the solution and examination advice for this question. A reminder that this video is in no way endorsed by VCAA. So for question 5 we have the function f with the domain of 0 to infinity, where f of x has the rule log e of x, and we also have the function g with the domain of all real numbers, where g of x is the parabola with the rule x squared plus 1. For part 1 of part A, we're asked to find the rule of h, where h is the composite function f of g of x. So h of x is going to equal the function f with g substituted into it. So that will be equal to the function f, which is log e of, and inside we'll now have x squared plus 1. So that is the answer to part A of this question. From the examiner's report we can see that this was very well answered, with 95% of students getting this correct. The few errors that did occur tended to be a result of poor notation, for example log e of x squared plus 1 without brackets included. So we still have the functions f of x equals log e of x and g of x equals x squared plus 1. So for part 2 of question A, we're asked to state the domain and range of this function h. So just over to the side we're going to do a few quick sketches of the graphs that we're dealing with in this question. So the first graph is f of x, which is log e of x, and it has an x-intercept here at 1, 0, and an asymptote with the equation x equals 0. Next up, we're also going to sketch the graph of g of x, and it was a parabola and it had a turning point at 0, 1. And now the composite function h, if we do that in red, is going to be the rule of log e of x squared plus 1. So when we put 0 into g of x, we get 1 out, and when we put 1 into f of x, we get 0 out. And as g of x is symmetric for the negative and positive sides of the x-axis, we get a sketch that looks something like this. So that would be the graph of h of x. So with that in mind, we can see that the domain is going to be dependent on the inner function x squared plus 1, and that gives all real numbers as being the domain of h of x. And we can see that from our sketch in red. And we can also see that the range is all of the y values that come out for h of x. And now because all of the y values that come out of g of x are greater than 1, we get all of these values being fed into our graph of f of x, and the graph that comes out from 1 to infinity for log e of x is all positive values and 0. So that's this range here. And using interval notation, that is 0 to infinity. So they are the answers required for part 2 of part A of this question. So that's the domain, and this is the range of the composite function. From the examiner's report we can see that 55% of students got no marks for this question, and only 15% got 2 marks for this question. The examiner's report goes on to state that a small proportion of students gained full marks for the question, and that poor notation was a contributing factor, but the main difficulty that students experienced was that of determining the range of the composite function h. A quick sketch over the given domain would have been helpful, and students are reminded that finding the domain and range are key aspects of a function. For part 3 of part A, we're asked to show that h of x plus h of negative x is equal to f of g of x squared. So to approach a question like this, usually we start on one side and see if we can show that the other side is equal. So starting with h of x plus h of negative x, we get that that would be equal to log e of h of x is just x squared plus 1, and then we'd add onto that log e of, and then it would be negative x all squared plus 1, and that needs brackets around the negative x. And when we square negative x inside the brackets, it just becomes positive x squared again, so this just becomes 2 log e of x squared plus 1. And then we have a log property that allows us to take up a coefficient of the log as a power. So that's going to be the same as log e of x squared plus 1 all squared, which is in fact just f of g of x squared. So we've shown that h of x plus h of negative x is equal to f of g of x squared. So from the examiner's report we can see only 31% of students got full marks for this question, and that the comment made was that many students were unsure how to present their working for a question like this. In the sample working shown above, both sides were operated on separately to arrive at the same expression, and the conclusion that one side was in fact equal to the other is valid. Poor notation was again evident. In particular, some students forgot the brackets around the negative x all squared that were required, as this, as it's written here, is not an equivalent statement. And for part 4 of part A of this question, we're asked to find the coordinates of the stationary point of h and state its nature. So there's two things that we're going to need to write at the end of this question. So we just need to remember that h of x did have the rule, which was log e of x squared plus 1, and that if we want to differentiate that, we will need to use the chain rule. And that's because there's a function inside a function. So for this, we can have y equals log e of the function u, where u is the inner function x squared plus 1. Then we calculate the derivative dy du, which is simply 1 on u, and you can look that up on the formula sheet. And du dx is simply going to equal 2x. So to complete the chain rule, we have h dashed of x is equal to dy du times du dx. So dy du is 1 on x squared plus 1 times du dx, which is 2x, which can be simplified to 2x divided by x squared plus 1. So that's the derivative of h dashed of x. Next we need to find the stationary point. So to do that, we solve h dashed of x is equal to 0. So therefore we're solving 2x divided by x squared plus 1 is equal to 0. And when we have a fraction equal to 0, just the numerator can equal 0. So therefore we have 2x equals 0, which means x equals 0 is the value of x where the stationary point exists. Next we can work out the y value by evaluating h of 0, and that's going to equal log e, and 0 squared is simply 0, so we get just 1 inside the log expression, and log e of 1 is 0, so the coordinates are 0, 0. Next we need to determine the nature of this stationary point, and this can be done in a variety of different ways. For this example, I'm going to show the use of a sign table or a sign diagram. So we're going to consider x values that are close to 0. So we're going to have 0, an x value just below it, which is going to be -1. You could choose other values, but that's a nice simple one. And a value greater than 0, which is +1. Then we're also going to need to calculate h dashed of that value, and then interpret the slope. And we're just going to arrange this into a table to make it easier to work with. So just a reminder that h dashed of x is the same as this expression over here. So h dash of -1 is simply equal to -2 over -1 squared is +1 plus 1 is 2, so that equals -1. So h dashed of -1 is -1, and it has a slope that would then look like that. H dashed of 1 is equal to 2 times 1 is 2 on the top line, and then 1 squared plus 1 is 2, which equals +1. And that means that its slope is going to look like this. And we already know that when x is 0, it was a stationary point, so its derivative is 0, and that's what we found at the start of this question, so its slope looks like this. Now looking at that sign diagram, it has a local minimum, so there is a local minimum at the point 0, 0. So that is the answer to part 4 of part A of this question. So from the examiner's report, we can see that 27% of students got full marks for this, and that other methods to identify the nature of the stationary point included the use of symmetry of g and log as an increasing function, the use of the range found back in part AII, the use of a graph, and the one that we showed, which was a sine table. So most students could equate the correct derivative to 0. However, many were then unable to solve the equation, forgetting that a fraction is equal to 0 when the numerator is 0. Of those who managed a solution, some overlooked the second part of the question or assumed that the stationary point was a point of inflection. So just a timely reminder to make sure that you've answered each part of the question thoroughly. Now we're moving on to part B, and we need to let k have a domain of negative infinity to 0, where k of x has the rule log e of x squared plus 1. For part 1 of part B, we're asked to find the rule for k inverse, the inverse function of k. Now before we go any further with this question, I'm just going to write myself a prompt that we need to express this as k inverse of x equals something, a rule, and that because it just asks for the rule, we don't need to find the domain just yet. In fact, that comes up in part 2. So the process of finding the inverse, the first thing we're going to do is let y equal the function k of x. So therefore we get y equals log e of x squared plus 1, and then we're going to swap the variables x and y to find the inverse function. So therefore we have x equals log e of y squared plus 1. And now we need to solve for y. So the first thing we're going to do is an equivalent exponential statement, which says that the base of log e remains the base, and we get e to the power of x is equal to y squared plus 1. And then solving for y, we subtract 1 and we get e to the power of x take 1. And then at that stage we'd have y squared, so to undo the squared we get plus or minus the square root. So y is going to equal plus or minus the square root of e to the power of x subtract 1. And now we're not quite done yet, as we need to decide whether we need the positive or negative part for this rule. Now to do that, we need to think back up to the original function of k and also consider its domain and range. So if we were going to quickly sketch k on a set of axes here, k had a domain of negative infinity to 0 with the rule log e of x squared plus 1, which is a graph that looks something like that, and it has a point here at 0, 0. So from there we could actually find the domain and the range of both functions. So if we start by finding the domain and range of k, we just swap them for k inverse. So the domain was negative infinity to 0 included, and the range, as we can see from our graph, is 0 to infinity. Now for the inverse functions, we just swap the domain and the range, so that the domain of the inverse function is now 0 to infinity, and the range is negative infinity to 0. And now the only way that we can get the range to be negative infinity to 0 is if we select the negative out of the two cases for what y was equal to. So this means the rule for k inverse of x is going to be negative the square root of e to the power of x subtract 1. So that is the answer to part B, part 1 of this question. So we had 16% of students get full marks for that question, and 65% of students got 1 mark. And the examiner's report goes on to say that the students appeared quite adept at the mechanics of determining the rule for an inverse, that is, swap x and y and then rearrange. However, few students took the care to determine the range of the inverse function and then select the negative root of their expression, which is what was required for the rule of k inverse. And that's what separated the students that got 1 mark and 2 marks in this exam. So for part 2 of question B, we're asked to state the domain and range of k inverse, which we did in fact do just a couple of slides ago. So looking at that table, we can see that the domain of the inverse function was 0 to infinity, and that the range was equal to negative infinity to 0. So they are the answers for the domain and for the range of the inverse function, which is what we were required to find for that question. So from the examiner's report, we can see that about a quarter of students got full marks for that question. The examiner had still described it as not being well answered. Most students utilised the fact that the range of the inverse was equal to the domain of the original, but found that stating the domain of the inverse function was far more difficult. Again, poor notation was evident throughout this question.